one bit full adder built in quarters using the logic gate, and we got input A, B, and C, and go into the XOR gate to generate the sum after we run the simulation. And you can see that sum actually goes high when odd number of inputs are 1. So this is the 4-bit ripple carry adder built using 4 identical 1-bit full adder blocks that we did just now. And actually this one, sum and also C out is the final carry, but we actually in this case, as stated in the assignment, we can ignore the final carry. So we actually see the sum, and here input A and B change in binary sequences, as we can see here. So C in actually is 0, so this is poor addition, and the sum waveform correctly represents the A plus B. So this is another one, the 4-bit subtractor, and this is also implemented using the full adder, as you can see here, and the subtraction is actually achieved using the 2 complement method, and each B input bit, as you can see here, is actually inverted using the NOT gate, and C in also got set to 1. So the full adder are connected in a ripple carry structure where the carry propagate from LSB to MSB. Also A and B, input A and B, they are changed in binary sequence, and C input C, we let it remain, we let it to become to 1. So this actually confirm the subtraction mode, and this is our output S. Show the correct subtraction result A minus B for each time interval. Okay, it's like this. Schematic diagram of the 4-bit XOR. Same, I will show the waveform of this XOR, and so this is the 4-bit XOR, and the output is 1 when both input bits are the same and 0 when they are different. And also same, now I will show the waveform generator. So you can see here A and B change truly the binary value over time, and we can see the output value is 1 1 1 1 when A equals to B. So it means that all bits equal. But when some bits of the A and the B is different, the corresponding bits in X will become 0. Okay, this is 1-bit 4-to-1 multiplexer using the N or N NOT gate. So input is the ABCD, and we got the select line. So actually only one input is allowed to pass. So input ABCD are actually held at fixed values, and S0 and S1 will toggle over time, and the up. So this is the 4-bit 4-to-1 multiplexer constructed using the 4 1-bit multiplexer blocks, and the function is also same like that. And the S1. So this is the 4-bit register built using the 4 DFIG blocks or DFF, and this is the waveform that generated. This is the waveform that generated. So initially its step is actually 0, so Q, you can see here is also 0 0 0, and when reset is inactive and clock inch or curve, Q will update to match T. Okay, so between the clock edges, Q will remain unchanged even if we change. So you can see here, this is the waveform generated, and from this waveform we can see that as S0 and S1 changes, the output X will switches accordingly to from 001 to 0. So this is 4-bit ALU design, and input A and A30 and B30 are connected in parallel to a 4-bit adder and the 4-bit subtractor, and an XOR block and XNOR block here. So all these blocks actually operate at the same time. So we now see the waveform. So this is the waveform created, and actually when the ALU cell changes, the output will also change immediately. So you can see here the ALU change sequence from 01 to 10 and to 11 to 00, and just repeat. And also during this, the output, this is the schematic diagram, output diagram that we already integrate all. So this is the 4-bit ALU system that we've output registering. So that we also got the 4-bit marks and ALU design, and we also integrate the register different for here. So this is what we combine all, integrate all. So I will show the waveform. So this is the waveform created. So we see the input A and B first, and actually input A and B are set to fixed binary pattern, so they remain stable. So, and the control signal is the A cell and B cell, and of course the ALU cell, they actually changes step by step, like from 00 to 01 and so on up. And the clock behavior is periodic square wave, and you can see the output behavior is the Q here. So like when the reset is equal to 1 and the Q is actually forced to 0 0,